the small change in x causes a change in y. But then because y changed a little bit, the whole thing is going to change a little bit. So you need to look into this in 2 steps. If we had a simple function to not a function inside a function, okay, x changed a little bit, the whole function changed. But because this is a more complicated setting, we want to split it in 2 halves. So there is a function inside a bigger function, but to simplify, we gave this a name. We called it y. And we keep in mind that y depends on x. So what happens here, we write it like that. So df dy times dy dx. So x changes a little bit. This is what it means. X changes a little. That's a small change in x. And therefore, y changes a little bit. So y changes a little because y depends on x. And because x changed a little bit, now y changes a little bit. So this is the chain. That's the chain rule. And therefore, the whole function, f, changes a little bit. And to find these, it's not a problem whatsoever. So this part, you need to take a derivative of this. So this part, you just pretend that the variable is equal to y. F of y equals y to the power of 6, right? So for this first part, you just pretend that that's the function. We called x squared plus x y. And therefore, it's y to the power of 6. That's how we imagine this. Nothing else matters for this moment. So to find the derivative, df dy, well, that's quite simple, right? We just use the power rule. 6 goes down. Y, 6 times 1 equals 6 times y to the power of 5. Right? So we will insert this result in here. But then also we need to take into account that what we call y is a function of x anyway, because that's x squared plus x. So for this part, we have h of x, or y equals h of x equals x squared plus x. But we know how to take the derivative of x squared plus x. So dy dx is just 2x plus 1. So the derivative of x squared plus x is equal to 2x plus 1. And now we just need to plug things back. So we split the problem in 2 parts and we just multiply. So we need to take this, plug it back here. We need to take this, plug it back here, and remember that we cannot keep y. We just insert the definition of y in terms of x. Alright, so now plug everything back. Plug everything back. The derivative of f of x is equal, the first part, so this guy, 6 times y to the power of 5. So we can just write it. And then we multiply by the derivative of y, the inner guy, 2x plus 1. 2x plus 1. And in the final step, we just remember that what we called y was equal to x squared plus x. So we just bring it back, because after all, everything needs to be in terms of x. That's the variable of interest. So all of this is equal to 6 times x squared plus x to the power of 5 times 2x plus 1. So this is the full derivative. And the notation that I used here is just to simplify, because you have something raised to power of 6. That's a very big power. And then you have a function here, x squared plus x. So why don't we treat it as a function inside a function? So we just say that I'm going to give this one a name. Let's call it y. And I will remember that it depends on x. And in the end, I'm looking at the derivative with respect to x. So what happens to all of this as x changes a little bit? Okay, so what's going to happen? X is going to change a little bit, and it's going to change this a little bit, what we call y. But then because y changed a little bit, the whole function is going to change a little bit. So it's a chain of events going on. This notation just helps us to split the problem into somewhat smaller components. And this allows us to first take a derivative here and multiply by a derivative there. And then just plug things back together. And then in the end, we write everything in terms of x. So let's have another example. So this was example H. Let's call it example J. And let's use the same principle. F of x equals, let's say, natural logarithm of 2x. Right? So far, we only knew how to deal with natural logarithm of x. And that's 1 over x. But we do not know how to deal with natural logarithm of 2 times x. So maybe it's not clear. So again, we can use the same notion. We can call this y, and we bear in mind that after all, it's h of x. So it's a function of x. It's a function of x. So then the derivative of this, which is df dx, is going to be given y df dy, but then we're going to multiply by dy dx. Because what happens here, x changes a little bit, then it affects what we call y, 2x, and because this y changes, the whole function changes. So again, we can simply take a derivative here, just pretending that the variable is equal to y. We know how to do it now. And then just additionally multiply by derivative of 2x. Okay, so for this part, what is this? Yes. So for this part, I'm just treating this as f of y, which is logarithm of y. So I'm looking this in isolation, and I'm just saying that I have a variable y. And I know what's the derivative of this. Logarithm of y has a derivative in 1 over y. So f of y prime is equal to 1 over y. I just changed the variable. Instead of x, I have y, but the derivative of logarithm of that is 1 over y. That's the same. And then for this part, I just need to remember that y, again, it depended on x. So this one here, and this one, was h of x, or y equals h of x equals 2x. So here the derivative of this function, 2x has a derivative of 2. So we just split the problem into two simpler problems. And now we plug everything back together. So all of this implies that f of x derivative is 1 over y times 2. And we need to remember that we defined y as 2x. So we just need to plug everything back. So that's 1 over 2x times 2. And this is 1 over x. Yeah? Is this a surprising result somehow or not? We got the same result as if it was 1 over x, or sorry, logarithm of x. That's exactly the same result, right? And I said that, or at least by starting this discussion, I implied that it should be somehow different. And we did it correctly. We did it correctly. We just got the same answer. And that's also another interesting fact. If you have a logarithm, and if you scale the unknown inside of logarithm by some constant, the derivative is going to be exactly the same. So we did everything correctly by performing the chain rule. So we had a function inside a function. One function is 2x, another function is logarithm, and then we did the chain rule. Maybe there is a simpler way to do it. Can you tell me if there is a simpler way to solve the same problem? Very quickly. Second solution. The function was this, logarithm of 2x. Yeah? So it's to that direction, it's not exactly outside. But you are right. We can use logarithm properties straight away by writing this as logarithm of 2 plus logarithm of x. It comes from the rule that logarithm of a times b, this we had 3 lectures ago, it's the same as logarithm a plus logarithm b. So that's a way shorter path, but then you need to spot something. So I guess this example is quite nice because it instructs us to think a bit more. So there are several ways to solve the same problem, and all of them are correct, meaning that they're leading to the exact same answer, but some of them are quicker if we are willing to, roll back the tape a little bit and to remember that if you have a logarithm and you have a product inside of logarithm, you can use the rules of the logarithm. Okay, so we just did it, and a very important fact when we wrote it like that is that logarithm of 2 is just a constant. It does not depend on x. This is just a constant. Which means that the derivative of this is equal to 0, right? Because the derivative of constant is 0, plus derivative of natural logarithm, which is 1 over x, equals 1 over x. So that's exactly the same solution. And we did it via the chain rule, or we do it by spotting this curiosity that we could have used the rules of logarithm from the beginning. So this pays off quite a bit. Okay, so let us have one more about the chain rule. So let's say we have example I. f of x equals to, let's call it e to the x squared. Right? So in the beginning of the lecture, we saw that e to the x, derivative never going to change. But now there is something else. It's not exactly e to the power of x, it's e to the power of x squared. So it's a bit different. So here, chain rule is very useful. So we can call this one y equals h of x. So we just prescribe a new variable. I'm just going to be calling x squared y, but I will remember that it depends on x, because after all, it's x squared underneath. And again, I can do the chain rule thing. I can use the fact that derivative, it's just product of changes. If you use the chain rule, it's df dx, and it's given by a change in the function caused by a change in y, but we keep in mind that y depends on x, so that's also a derivative of y with respect to x. Right? So chain rule, or especially doing chain rule in this way, it's just a change of notation that helps us to track what's going on here. When you become a bit better at this, you do not need any of that. You just see what's going on. But then you need to spend a bit of time and practice. But if it's not clear, I just say give this a name, any name, and just keep in mind that it depends on x anyway. And if the derivative is change in the function caused by change x, then it goes in a very concrete way. X changes a bit, it causes whatever you call y to change, but then because y changes, the whole thing changes. And we just need a product of that. So again, for both parts, we just work individually. We're going to work this out, we're going to work that out. And for this part, I just treat my function as a function of y, and this is equal to e to the power of y. And I need a derivative of that. So if the function is e to the power of y, then the derivative is exactly the same, e to the power of y. Nothing changes. And for this part, I remember that y depends on x. So y is equal to x squared. So then the derivative of, I think it's always better to write y was equal to h of x, because that's a function of x, and that is equal to x squared. So then the derivative of h of x is equal to 2x. Right? So derivative of x squared, 2x. One of the first derivatives we learned. So we worked out individually, we plug everything back, and we remember that we always need to substitute back y in terms of x. But we know what y is. We declared y x to the power of 2. All right? So, let's plug it back. Plug it back. So the derivative of this, then it's equal to e to the power of y times 2x. And just remember that y is also in terms of x. It was x squared, 2x. Like this. Yeah, so we have a product. So we keep track of what is going on. And again, maybe now, at this very moment, when I solve it, it might seem very puzzling, but you go back home, you work through a couple of examples by using this simplifying path so that it allows you to keep track of what's going on. But then after a few iterations, you're going to see that you don't need any of that. You do not need any pointers. It's going to go quite automatically. You're just going to notice that All right, here I have some strange function because we are raising to the power of 6. So, okay, I'm just gonna do the derivative as if this does not change. So, I'm gonna do 6 times whatever that's inside the power of 5, and then inner derivative. So this is gonna come for sure if you just keep on working on it. All right. So we can do one more, and then we can talk about a couple of other things. So let's say we do. So let's say we do this one again. Let's call this one maybe example K. F of x. This is something that again can be solved in a couple of ways. Logarithm of x squared. Clearly a function inside a function. So we have a logarithm, and inside the logarithm it's another function, which is y squared. So you can, again, solve it in 2 ways. One way is indeed to use the chain rule. So let's do that. Let's call it 1. And then let's say I have the derivative of this. So this is 1 equals h of x equals x squared. So I have the derivative with respect to x. That's just little change in f caused by little change in x. And then it's going to be derivative of f with respect to y, and then I'm going to multiply derivative of y with respect to x. So for this part, it's going to be equal to, well, we treat a function of y, which is logarithm of y. So then the derivative of this is 1 over y. Now for this part, I know what y is. Y is a function of x, and that is x squared. So the derivative of this h function is just 2x. So I got this part, I got another part, and now I can just plug it back. So plug back, which means that your derivative is given by 1 over y times 2x. But you need to remember to substitute back what y was. So this is equal to 1 over x squared times 2x, which means that x cancels out against the square, which gives 2 over x. That's the derivative, 2 over x. Okay, so that's the chain rule. When you recognize a function inside a function, split into 2 problems, take derivatives separately, multiply at the end, and you get 2 over x. But by remembering the logarithm properties, can someone help me how to simplify this from the get-go? Yes. So we could have spotted the fact that logarithm of x squared is the same as 2 times logarithm of x. And now here we have the whole separate rule for this. If you have a logarithm multiplied by any constant, the derivative of this is just going to be that constant over x. And that's just one step. So it always makes sense, and it always pays off to see if you can simplify it. And you can simplify it if you have logarithms. So if you have a function inside of a logarithm, most likely you are able to split, most likely you are able to move something around, and then you do not need to do the chain rule. If you don't remember the properties of logarithm, then there is always a way through the chain rule. So by the rule for logarithms. All right. So really, we did quite a few examples. But I want to finish the class with illustrating some also important applications. And from now on, we're going to explore one big application, which is optimization of a function. So how to find maximum, minimum using derivatives. So I'm going to dedicate the whole separate lecture for that. But let's start with another task. So derivatives help detect where a function, f of x, increases or decreases. So it really helps to analyze a function. Maybe the function is complicated. For instance, in exam, maybe I'm asking you to analyze something like this. It's not very convenient to sketch the graph of this, not at all. But with derivatives, it can be way easier to analyze. If I'm asking you to answer the question when the function increases or decreases. And indeed, we need to look at derivatives. So if a derivative of a function is either positive or zero, so non-negative, then the function itself increases. If the derivative is smaller or equal to zero, function decreases. Well, if we are at this point where the derivative, sorry, I forgot the derivative, so where the derivative is equal to zero, then f of x, so the function is it neither increases nor decreases, which means that in effect it's stabilized. It stopped changing, which implies that it either reached its maximum or minimum. So we're going to dedicate a bit more time to this third case, but I want to start with these two. It's neither increases nor decreases. Okay, why is it the case? So remember that a derivative is the slope of a tangent line, geometrically. So let's say I have a point somewhere here, right? So let's just call it the same graph that we have. And let's say I draw a tangent line here, right? What can we say about the slope of a red line without knowing how big the slope is? But just from this picture, what can we say about the slope? Positive, yes, positive. This, for sure, we do not know what size it is, hell knows, but it's clear that the slope is positive because this line is going upwards. That we know. And clearly, because the slope, it is the derivative at this point. If the slope is positive, then we detect that the function is climbing up because the tangent line slopes positively. It goes upwards. So then, indeed, at this point, the function is increasing. same. I mean, we do not see it in this picture, but vice versa, it decreases. Well, or if the slope is negative, then it decreases. And that's just vice versa. So let's try looking into an example. So you have a question. Where does this function increase or decrease? And let's start with a simple example. Let's have f of x equals to 2x squared minus 8x. Right? So nothing fancy so far. I hope you see that we do not need here any chain rules, quotient rules, anything. Quite a simple example. So I'm asking where, so what interval in terms of x, where does this function increase or decrease? Function, one function I mean. Increase, decrease. So we need to look into derivative. Someone is losing all the drinks there. Alright, so let's look at the derivative, f of x prime. So we can find the derivative of this, not an issue. I hope you see that this is going to be 4 times x minus 8, right? Because we have a sum or a difference of two functions, but that's not a problem for the rule. If you have a derivative that is defined as a difference, then the derivative of a difference is difference of derivatives. That's the same thing. So we take derivative here, which is 2 times x, and the derivative of 8 times x is just 8. And I need to solve an inequality. So 4x minus 8 greater or equal to 0. So I need to solve for values of x for which this derivative is positive. So that's a very simple inequality that we know how to tackle. It's a linear inequality. We can just move 8 to another side, and we can divide both sides by 4. Which means that if x is greater or equal to 2, then the function is increasing. When it's exactly equal to 2, then the function is neither increasing nor decreasing. So when I'm asking you to find, the interval where the function is increasing or decreasing, then it doesn't really matter. You can just write strict inequality as well, because we can treat the case of equality separately. That it neither increases nor decreases. So for these x values, f of x increases. Clearly, to find another case when it decreases, we just need to flip the inequality. We need to find where this is, where the derivative is smaller or equal to 0, which is 4x minus 8 smaller or equal to 0, which is the same answer with the flipped side. x needs to be smaller than 2, smaller or equal to 2. When it's equal to 2, it's going to neither increase nor decrease. Right, so for these values, the function decreases. And we can check it. Visually. Well, I guess it's not this picture, sorry. I think it's this picture, yes. So this is how this function looks like. That's how it looks like. This is f of x equals to what was it, 2x squared minus 8x. And you see that up until 2, so this is x equals to 2, we see that for all these values up until 2, the function is decreasing. If we were to draw tangent lines, the tangent lines, they have negative slopes. When we go to the other side of 2, the function starts, for all these values, the function starts increasing. Like this. Function starts increasing. Should we draw any tangent lines? Sorry, like maybe here. They all have positive slopes. So positively sloping tangent lines, because the derivative is positive at every point above 2. So we're going to go through more examples like that in next class, but I want to finish with this. Do you remember how we call such function that looked like a smiley face? And especially, what was the property where I can take any 2 points and I can connect them like that? We had a name for such function. Remember? It was called convex function, right? So if I can take any 2 points on the graph and I can connect them, and then all these lines staying above the graph, the function is convex. So this is a convex function. I can sometimes ask you, can you tell me, I can give you a function, and I can ask you, for what values of x this function is convex or concave? Again, if you manage to draw the graph, and then you find where you can do this trick visually, then maybe this is where the function is convex or concave. But the information about convexity or concavity of a function, this information lies in second order derivatives. So let me just look for this very specific function. Second order derivative, which is literally, it's denoted as f with a double prime, meaning that we took the derivative 2 times. So it's a derivative of a derivative. Derivative of a derivative. And if second derivative is positive, or greater or equal to 0, we can do it like that, we have that the function is convex. If second derivative is lower or equal to 0, we have that the function is concave. For those x values, it's concave. So very quickly, looking into this function, I took a derivative and I got 4x minus 8. So f of x was equal to 2x squared minus 8x. The first derivative was equal to 4x minus 8. The second derivative is just derivative of this. To do it again. Take what you have, do it again. I hope you see this is equal to 4. Right? The derivative of a derivative is equal to 4. It's strictly positive number, meaning convex function. So you can find whether function is convex or concave by looking into the second derivative. And we see that indeed for this function, it is convex. So all of these line segments are above the graph. But it could be very difficult to figure out without any analytical tools. But with the second derivative, you can update that information as well. So second derivatives are going to be very important for us when we talk about maximization or minimization of functions. So this we're going to take up on Monday. So I'll see you then.